Thank you, Yugang, and thank you, Zhugang, for giving me a chance to talk in Fudan, although online. I was in Fudan several years ago. I hope to visit again in the future. Okay, the title of my talk is The Structure of Heavy Tetraquarks and Their Production in Heavy Ion Collision. I will mainly discuss the structure of X3872 and TCC, which was recently measured, and try to make a general argument on their structure, starting from a quark model point of view. And this is a collection of many works, but the most recent paper is in the archive here. I would like to thank my group members and external collaborators. Okay, so starting from X3872, we have seen a lot of new exotic states. The recent publication by the LHCb collaboration, which summarizes their new hadrons that they found, more than 60, most of them, all of them heavy quarks, and many of them have exotic, probably exotic quark numbers. I will, of course, not go over all of these. And of particular interest to me is XTCC, because they are close to the lowest threshold, and maybe they may be easily found in heavy ion collisions also. So we know the point of my talk is we know quark model explains the ground state meson and baryon masses very well, and hence states involving similar sizes. We know that the dynamics involving similar sizes should also be could be understood from a quark model point of view. So therefore, from that respect, what does quark model tell us about the compact typical hadron size of multi-quark states? That's our technical. Just a few reminder, ground state in a quark model, the ground state is the orbital angular momentum is equal to 0 state. And we have pions and vector mesons. The only difference is their spin orientations. On the other hand, these are well described, but on the other hand, as we go to P-wave mesons, things become slightly more complicated because they are excited states. For example, in the P-wave, for example, A0, F0, you have S1 and also L1. But then you can also have produce this quantum number with 4 quarks, 2 quarks, 2 antiquarks, namely 2 strange quarks, because of the masses. And then actually you get a similar mass to what you get from a quark model, 2 quark model point of view. Or you can also get similar masses, assuming these are K-clever molecules. And this picture has been around for a long time, but still not definite conclusion as to the structure of this hetero state, for example, or F0 state. One interesting measurement by Alice collaboration is they measured F0 recently. And according to their measurement, if these are true, they should have SS bar and somehow follow the strangeness enhancement pattern. What they find is somehow they are consistent with this kind of 2 quark picture. Although this is only based on P-led collision, so future measurement by Alice of F0 in heavier nucleus collision would be very interesting. Anyway, my topic is, as I said before, where is the compact exotics, and we would like to understand whether we can have compact configurations and study this question in a quark model point of view. So let's start with nuclear potential. Nuclear potential is the relative distance between the nucleons in the isospin 0, spin 1 channel. They are repulsive. This is a famous potential. And this has been indirectly or directly shown to be true by recent collaboration. They've been working this for a long time now already. And as you can see, as the distance between the two baryons decreases, the potential increases. So therefore, you obviously don't expect to see, for example, a 6-quark state or dibaryon state in this channel, because when you try to put them together, this repulsive force will forbid them to become complex. On the other hand, if you increase the flavor to 1, then you will see that there are channels that appear which are attractive. For example, in the flavor singlet channel, flavor 1 channel, the baryon potential becomes attractive. And of course, in the flavor 27, it's still repulsive. Therefore, if there is any hope of observing a multiquark or a 2 baryon potential, then it would be in the channel where the 2 corresponding mesons, or sorry, baryon, when you put them together, you'll have an attraction. Then there's a hope that we will have a compact configuration. So let's analyze this from a quark model point of view. So let's consider, for example, putting 2 baryons closer together, and then try to understand what happens, or the energy dynamics, starting from a quark model point of view when they are compact. From a quark model point of view, you start with the kinetic energy of individual quarks, relative kinetic energies, and then you have 2-body interactions, usually denoted by IJ. This is the so-called color interactions, something like the Coulomb type of interaction. And in fact, the linearly rising potential also resides here. They depend on the total color of the 2 quarks in 2-body interactions. And another important feature, at least when analyzing the ground state, where the P wave is not so important, is the so-called spin-spin interaction. It's just like the magnetic interaction, where you not only have color, but also spin, determining the short-range interaction. And then you also parameterize the potential. And for example, if you just use light quark masses around phenomenological quark masses around 300 MeV, strange mass 500, charm quark 1500 MeV, then actually these simple calculation quark model gives you well describes the ground state masses of baryons and also their mass differences. Now let's try to understand what happens if you put these 2 baryons together. And obviously, the first thing that you note is that compared to 2 separate baryons, if you try to put them together, you have an extra kinetic energy coming in, extra kinetic relative energy. And that's the, of course, the relative kinetic energy that you see in a 2-body problem. And that extra kinetic energy is larger than 100 MeV, of course, depending on the relative size or size. But if you want to put them together in a usual hadron size, or a nucleon size, or dibaryon size, then the relative kinetic energy that you have to overcome should be more than 100 MeV. So that's the typical repulsive energy coming from the repulsion, and which has to come either from the color-color interaction or color spinning. So let's start with the color interaction. That's the usual Coulomb type or linearly rising type potential. And these are really coming from the 2-body interactions involving quark I and quark J. But suppose all of the quarks have similar masses and therefore occupy similar spatial sizes. Then the relative distance between any 2 quark pair should be similar. So therefore, this would be a universal function independent of the relative distance between different flavors, different quark. So therefore, what is really important is whether you have an attraction or not really depends on this factor, the summation of this factor, assuming this universal. And you can see that if you sum over the all color-color interactions between quarks, then this color-color factor is the color factor involving these two quark pair, this two quark pair, this quark two pair, and so on. It's like all the color factors involved. And there is, of course, this famous formula where this is just equal to the sum of the total color of this configuration minus the color of the individual sources color. Now, if you have a color singlet configuration, if this is a color singlet configuration, then the total color is 0, and therefore you just subtract out the individual strengths of the single quark charges, which is equal to the number of quarks in the total configuration. But the number of quarks in the total configuration is just the number of quarks in the individual baryons, two baryons. So therefore, what that means is this color factor is just the color factor among these two baryons separately, and there is no color contribution coming from color factor coming from one coming from this quark, this baryon, and one quark coming from the other baryon. So therefore, the extra color factor or color interaction that you expect as you put them together cannot be very strong. You can naively understand this. Why that is so is because this is a color singlet. So therefore, even if you come with the colored charge, this colored charge, if you sum over the interaction of all these color singlet sources, will not have such a strong interactions. So that means if you want to have a larger section coming from these color interactions, assuming all these quarks have similar masses, you cannot possibly expect to have large contribution coming from the color factor. Of course, you can have distorted distribution and have dipole, but then for ground state configuration, this distorted configuration, you have additional configurations. So therefore, you don't expect to have such a attraction coming from this point, at least for similar quark masses, quarks. So therefore, let's look at the second term. If you look at the second term, this is the so-called color spin factor. And again, assuming all the quarks have similar sizes, let's forget about this universal factor, which is independent of each quark pair you look at, assuming they are similar sizes. They typically are proportional to this color factor and spin factor. And this is depending on whether you look at the quark antiquark or quark, depending on the total configuration of these two quarks, because these two quarks can have color, flavor, and spin. If you look at the maximally antisymmetric configuration, this K factor is negative. And for the quark antiquark, the most attractive channel is, of course, the color singlet spin zero state. That gives you something like -16. So therefore, if you this factor gives you most attraction in the quark antiquark channel in the color singlet. On the other hand, even if you have a quark, they have an attractive, maximally attractive good biquark channel. This is not as large as this, but nevertheless, this is good enough to give you possible attraction, even if you have only quarks. This K factor is, as I said, when it's negative, it gives you an attraction for that configuration. And if K factor is larger than 0, it gives you repulsion. And in the simplest quark model, this K factor, in fact, is the reason why there is a mass difference between delta and proton, because delta, all the spins are aligned in the same direction in the lowest picture. And proton, you have one quark pointing in the other direction. You can calculate with the full wave function the K factor for delta and proton. Then it turns out that for the delta, the K factor is 8. And for proton is -8. So therefore, this is attractive, this is repulsive. And therefore, the K factor difference is something like 16. So this is assuming universal. What I can expect is if you have a K factor of 16, that gives you the mass difference between delta and proton, which is 290. So K factor of 1 gives you something like 18 MeV repulsion, naively assuming they have similar sizes. Because after you multiply this K factor with this additional factor, you get 290 degrees, so 290 MeV for 16 K factors. So to begin with, it is important to see whether the compact configuration that we want to see has a positive K factor or negative K factor. And if this is negative, and if this is very large, something like 8 minus 8, then there is a possibility to overcome the repulsion and might have a compact configuration. So this K factor, in fact, is very important and captures many of the characteristics that you, in fact, see in the lattice calculation for nuclear protein. If you look at the lattice calculation very carefully, there is a difference in the spin 0 and spin 1 channel. The spin 0, the isospin 1 channel, is slightly more repulsive at short distance, systematically, compared to the spin 1 channel. And this ratio is something like 1.2. And in fact, the K factor that we obtain in these two channel difference is also something like 1.29. The baryon, H baryon channel is, as I said, is objective. This K factor, and if you take the ratio between the 27, is -3, meaning one of the channels should be negative. And in fact, this is what you more or less observe in the lattice calculation. We, of course, did the more sophisticated calculations to do a full quark model calculation and compare with the lattice. And I will not go into detail, but what we find is the different flavored channel, if you take the ratio at least, as you approach the short distance limit, this is the distance. This is distance between two baryons, and the lines, solid lines, is with symmetry breaking. As you see, symmetry breaking without symmetry breaking. The black line is symmetric. Red is broken. It turns out that the lattice calculations, when the two baryon distances approach 0, they approach the K factor that I calculate, or the full lattice constituted quark model calculation ratio that one can calculate in the quark model. So therefore, this more or less, in fact, the K factor already gives you a good description of this ratio at short distance, even for all the different channels in the channels. So having learned that, we can ask why heavy quarks are needed for compact exotics. The reason why all the LHCb calculations, or why people, or even our group, advocated heavy quarks for possible compact configuration follows. In fact, this slide, this point was made earlier by Carliner and Rosner. And the fact is, when you now introduce heavy quarks, there are, of course, differences from what I have talked before. Because if you have heavy quarks, then what I said is the difference, the distance between heavy quarks and light quarks, I assumed was similar. But in reality, the distances between heavy quarks and heavy light quarks, or light quarks, if you put them together, are in general different. This can be easily seen because, for example, just look at the two-body problem, assuming a Coulomb potential. If you have a 1/r potential, then the Bohr radius is 1/r square, energy is mg square. So therefore, the distance obviously depends on the quark masses. So therefore, even the color-color interactions between C and another quark, for example, color singlet, will be different whether you have a quark anti-quark who is heavy or light heavy or light light, because their relative distance are should be different because of this mass factor. So, for example, if the color state of CC is objective, then this means that the lambda factor is 0, and also the relative distance between C and C, or C compared to CC, C light quarks are different. So therefore, what used to cancel before will not cancel anymore. And if this heavy quark distance is smaller, then obviously this is dominating over the repulsive channel, which, if they are in the color singlet channel, used to be 0, will not be 0 anymore. So therefore, we will have an extra. So therefore, you can have extra attraction if you have a heavy quarks, and if especially the heavy quarks combine into a attractive lambda. Another important, very important point is the color spin interactions, because this is the color and between quark, and this is the color spin interaction between quark and quark antiquark. As I said, the quark antiquark attraction in the most attractive channel is larger than the most attractive quark channel, and the reason why that causes a problem when you try to put for example, a tetraquark, quark antiquark configuration. This black dot is a quark, the empty is a antiquark. So therefore, you have a quark, antiquark. Now, if you have a quark antiquark, then the most attractive channel here is 16. The most attractive quark channel is -18. So therefore, if you try to put them together, instead of this quark trying to come together, they will just fall apart into a meson, two separate mesons. They will just fall apart. On the other hand, when you have heavy quarks, these color spin interactions are usually scaled with constituent quark masses. So therefore, for example, if you have a quark which are both heavy and antiquark which are light, then the attractive channel, which was responsible for this tetraquark states to just fall apart into a meson configuration, will not fall apart, because now the quark antiquark attraction is scaled by the heavy quark masses, whereas the large diquark attraction still remains. So therefore, instead of falling apart, they would like to come together into this diquark configuration. So there is a possibility that this diquark, instead of just falling apart, will form a compact configuration. So therefore, that's why sorry. Okay. This was the original motivation why those so-called TCC could be attractive and form a complete configuration. That was first advocated by Richard and Arnold in the 80s. So indeed, because of these two reasons, possible attraction coming from heavy quark configuration in the color configuration, and this attractive, this less attractive quark antiquark configuration, if one of the quarks is heavy, was responsible, is one of the reasons why you need heavy quarks, and for this compact configuration possibly exists. So therefore, in fact, indeed, many heavy exotics were found. But the point is, although many exotics were found, it is still not clear whether their structure is really this compact configuration, or they just fall apart, but form a molecular bound state through pi meson exchange. And if you have a pi meson exchange, their relative distance should be much larger than a compact configuration expected for this kind of quark dynamics motivated. So therefore, it is not clear about their structures. So as a representative comparison, to check whether something is multiquark or loosely bound molecules, we will look at the X3872 and TCC 3872, which is simply measured, and ask the question, can they be compared from a quark model point of view? As I said, from a quark model point of view, the most important point is the color-color interaction and color-spin interactions. So let's start with the color-spin interaction and calculate the K factor when you have something called the X3872. Now, X3872 is, they call high state these days, but anyway, I would like to just stick with this name for the time being. The expected isospin although isospin is broken because of very slight quark mass difference, and it's important, but nevertheless, let's just take isospin to be 0 for the moment, and the JPC to be 1 plus. Then, in order to obtain this configuration, you can get a quark, 4-quark configuration and obtain this quantum number. And it is best to construct these quark states in the so-called quark antiquark times quark antiquark basis. So you have a CC bar times a QQ bar basis. Now, in order to have this charge conjugation plus state, you have to have either this is color and spin. So the first number is color. This is color singlet and spin 1, and this is color singlet, spin 1. So you have to have color singlet, spin 1, color singlet, spin 1. Or you can have color octet, spin 1, and color octet, spin 1. These are the only two configurations, assuming there is no P-wave contribution. This is the only two possible color spin bases that you can construct this, with which you can construct this quantum number. Now, so therefore, I will construct the so-called K factor, assuming for the moment, assuming all the wave functions occupy similar sizes. Then you will find that the so-called color singlet spin 1, color singlet spin 1 is a repulsive channel, so you don't expect to have any repulsion attraction coming from this configuration. But there is a slight attraction coming from the color octet spin 1, color octet spin 1 configuration. And this is something like minus 20 MeV. But as I said, in order to form a compact configuration, the minimum amount of attraction that you must have is larger than 100 MeV. So therefore, this is far from strong for this configuration to be compact. This kind of attraction is not strong enough for this to be a color singlet. So therefore, but nevertheless, if this is compact, then this should come from this configuration, because this is, as I said, too repulsive. So if you try to put them together, they will favor this configuration. So which means that CC bar would be in the color octet, spin 1 channel, QQ bar would be in the color octet, spin 1 channel. So therefore, we took, if you look at the spin 1 color octet channel, and then see whether this small CC attraction is large enough, we find that this is not, because if you have a color octet CC configuration, color octet is repulsive. You can work out the Casimir, this color factor, when this is a color octet, single color, then subtract each color factors, then you will see that this is a repulsive color configuration. So therefore, at short distance, this is repulsive. So instead of giving an attraction, when these are compact configuration, they will just give you repulsion. So therefore, you don't expect to have any additional attraction from the color configuration. What that means is whether you look at the color configuration or color spin configuration, you will never expect this X state to be a a compact configuration. There is no way this could be compact. So therefore, one can naively say from previous tested quark interactions, this probably cannot be a compact multi-quark configuration. On the other hand, if you look at the TCC, in this case, because of the isospin 0 and because of the dominant attraction, in this case, it is better to view this quantum number in the quark-quark, anti-quark basis. In order to generate this quark number and assuming no p-wave contribution, again, there are only two Fock spaces in the color spin basis. And this is the so-called color spin. So this configuration is color anti-triplet and spin 0. And this configuration could be color triplet spin 1. Or this could be color sextet spin 1, color sextet, and this could be color anti-sextet spin 1. Now, again, this is repulsive. On the other hand, this is attractive. This is attractive because this spin 0 is the most attractive diquark channel. And this large diquark attraction gives you indeed some attraction. Of course, here you also have off-diagonal components, so therefore you diagonalize. The attraction is in fact larger. Furthermore, because the spin favors this configuration, if you now look at this configuration, as I said, this configuration, spin 3 bar S0, and this is spin 1. This color triplet or anti-triplet are also attractive channels. So therefore, you will have extra attractions coming from the color-color interactions. So therefore, both color-color and color spin factor gives you an attraction, which could, in fact, overcome the repulsion that you see when you try to put them together. So therefore, there is a possibility that this TCC could be compact. In fact, if you, instead of using C, but use B quarks, because of this reason, all of the quark model predict that they really are compact TBB states. On the other hand, if you do a realistic calculation with Z quarks, the attractions that you get from the two mechanisms that I just described is really not so clear. And therefore, let me talk about this a little bit later. And what you will find, as I said, that this is a complicated table, but this is a full quark model calculations. This is the color-color interaction. As I said, if you have a color-color, the dominant configuration for BB is indeed gives you an attraction compared to this. And the so therefore, indeed, this is a color, and this is smaller for charm quarks. So therefore, for heavy quarks, this color-color interaction gives you attractions, and also color spin attraction gives you attractions. So therefore, this is attractive, but then instead of using one basis and full basis, also there's a difference. If you look at the full calculation means one basis means just a variational trial wave function with one Gaussian, and this full calculation is using a full wave function, all possible configuration. So therefore, you will see that the attraction that you full mass that you get is really important that you do a full model calculation. So if you do a full model calculation and take into account all color-color interactions, then TBB is attractive. You have a bound state compact configuration. And TCC is still controversial. So it's not so clear whether it really bound or not. And this is the graph that LHGB collaboration showed when they measured this for the first time. And this is all the quark model calculations and other model calculations. It's really depend on the detailed quark model calculation. So what we can conclude is TCC could be compact. It's still not completely sure, because if you change the parameter slightly or change the form of the potential, this could be compact or maybe not compact. But what we can say is X3872 cannot be compact. This is certainly true. So that's the first conclusion that we can draw. So therefore, if this cannot be compact, and this could be compact or cannot be compact, why do we measure this? And if this is not compact, what are the two possibilities? And for that, we go back to this lattice calculations, which shows that this is the relative distance between D and D star, which comprises this quantum number and the meson content. And you will see that there is an attraction when the distance between D star gets smaller. And this is also, in fact, what we find in the quark model calculation at very short distance, and mostly coming from the color spin and color interactions. So you have an attraction. That's one point. Another point is when you have this quantum number, with one meson, another meson, and where the total quantum number is isospin is small, but the total angular momentum is not zero, total spin is not zero, then what you typically have is so-called SD wave mixing to ion exchange. Now, what that means is if this isospin is zero, then there is a D wave mixing, and if the spin is non-zero, and what that means is the following. If you try to construct the potential between this state and this state in the heavy quark limit, then because of these quantum numbers, there is the mixing between the so-called S wave state and D wave state. What that means is this is assuming the orbital angular momentum between H1 and H2 is zero. But if you have a pion exchange, then the intermediate state is a D wave state, spin 2 orbital angular momentum state. And you can have a mixing between D wave state and S wave state because of the quantum numbers. And this is precisely what you will see occurring, which was first obtained by Thornquist in the both TCC channel and X channel. And this is a so-called off-diagonal element, which when you diagonalize gives you a mixing. And what we find, what he actually find is that for X3872, this D wave mixing is strong. So therefore, even if you do not have any central potential, the D wave mixing is in fact good enough to give you a bound state with very large radius. And for TCC, if you do the similar calculations, the D wave mixing is smaller. On the other hand, as I said, at short distance, there is an additional D star attraction. So therefore, if you combine D star attraction and at short distance and the D wave mixing, they together can in fact give you also very large molecular configuration. This mechanism is very similar to what you see in the deuteron, because of the same mechanism. In deuteron, you have S wave state and huge D wave state mixing in the total wave function. And that's precisely what you also see, assuming you solve this potential problem, D wave mixing. You have a large S wave, then non-trivial D wave contribution, which gives you also a very large radius, similar to deuteron 2.1. And also for TCC, D wave mixing alone is not strong enough, but assuming a short range attraction, this short attraction, although it cannot, even if it doesn't give you a compact configuration, it will eventually give you a molecular configuration. It is possible that they will eventually give you molecular configuration with the D wave mixing, and D wave mixing also gives you a large attraction, a large distance wave function. So therefore, what we can conclude is the following. X cannot be compact, but these are most likely a molecular configuration, large radius, very similar to the deuteron. And TCC could be compact and or could also be molecular configuration. And because this molecular configuration is because these are very similar to the deuteron, and whether if we can confirm this X is indeed a molecular configuration similar to deuteron, and TCC is a molecular configuration, or if it's not a molecular configuration and compact configuration, and we will really will be able to discuss detailed properties of the TCC and understand, have a new constraint of quark model interactions at co-distance. Will be a new think ground of quark model and QCD dynamics for multi-quark configurations. So therefore, let's try to see whether we can see these kind of things and discriminate whether TCC is a multi-quark configuration or compact configuration or a molecular configuration, and confirm whether X is a molecular heavy ion collisions. So that's why we are interested in measuring exotics in heavy ion collisions. In 2008, in fact, before LHC heavy ion program began, just before, there was a conference at CERN, heavy ion collision LHC, last call for prediction, and there was a conference in 2007, I think, because this paper was published in 2008, and they have there was held at CERN in June of 2007. Many people came. I also went there and gave a contribution. And in fact, I have a contribution in that journal, and it was charmed exotics from heavy ion collision. And I already discussed these kind of things in 2008, and I also even discussed that it would be interesting to measure TCC. And as you know, TCC was indeed observed later, recently, last year. And a few years later, we wrote a PRL because I was staying in Japan, and we had some molecular type workshop, and we found that depending on whether X, for example, is compact or molecular configuration, if it's compact, then the production is suppressed. If it's a molecular configuration, their production is not suppressed. Would be the production rate would be similar or larger than the statistical frequency. That's what this band tells you. And recently, CMS collaboration measured X3872, and what they measure is compared to PP collision. When you go to lead-lead collision, the ratio of production between X and psi2s suddenly increases. Maybe it's related to this, although it's not conclusive. We have to still work on this. So let's see why the reason why we said that the production really depends on the size is the following. If you look at the coalescence model, if you have a two-body coalescence, then you have a Wigner function. That's the wave function that we have. And this is the individual distribution of the first constituent, second constituent. This is a delta function. And it is very important that you normalize them properly. If you don't normalize it properly, then you make a very different prediction that really tells you nothing. So the normalization condition is that if you have to calculate over the phase space, and it gives you the total number of first constituent. This is the first normalization condition. Another important normalization condition is that when you use these Wigner functions, if you neglect this, then the Wigner function has to be normalized in the appropriate phase space. Phase space meaning momentum space and X space. If you don't do this, then you can get a very varying predictions. Now, the Wigner function, usually people use Gaussian because that's the simplest to calculate. And usually we have realized with Chen and other that Kayson, that it would be best if you calculate this Wigner function. When you calculate this, you go to the rest frame of the Wigner of the molecule and then calculate the coalescence property. If you do this, for example, one limit is the so-called sigma going to infinity limit. This limit is when you assume that the wave function of the final deuteron, for example, is very large. Then this formula just produces to just multiplying the proton distribution, neutron distribution, PT distribution. So the PT distribution of the deuteron is just factors coming from this times if this is the total momentum of the deuteron, then it's half the transverse momentum for the first neutron and half of the second neutron. That gives you the sigma infinity limit. In fact, many experimentalists just use this formula. Now, the reason why we say, nevertheless, the reason why sigma is important, the size is important, is the following. If you just look at this formula, as I said, if there is no other scale, then this just gives you normalization condition, so there would be no size dependence. On the other hand, this distribution is usually exponentially decreasing or power law in the large PD direction, so therefore there's an additional scale coming in. And because of this additional scale, this coalescence formula gives you something like this. And this additional scale, just to give you a handle of what is going on, if you assume this transverse momentum to be thermal, for example, then this extra scale temperature, when you put it into this formula, gives you a correction factor in the sigma infinity limit of this form, which, as you can see, if sigma becomes very small, then for Tm fixed, if sigma becomes very small, then this becomes very large, so therefore there is a significant factor. This becomes visible when the T temperature is 150 MeV and mass is 2 GeV, then as long as the compact size is very small, then this kind of factor gives you very now, so let's try to, since, as I said, if this is indeed the molecular configuration, then their structure is very similar to deuteron. Let's see whether this simple formula fits the deuteron very well. So what we use is we use a proton distribution as the transverse distribution of one of the constituent. Then the deuteron PT dependence will scale like RB, because when we use the proton distribution in the coalescence formula, we do not use the proton distribution that's observed, but scaled, because when they form, there would be they will form earlier than when the final, all the deltas and all these feedbacks have contributed to the final proton distribution. So this RB factor takes into account the feedback effect. Before feedback, the deuteron would be formed, so RB. Then the deuteron and helium-3 will scale differently as a function of RB, the scaling factor, because deuteron will scale like RB square and helium-3 will scale like RB to the cube, assuming helium-3 is composed of 3 scaling factors as distributions, using the same coalescence formula for 3-body coalescence. This is the statistical factor. And then this volume is the coalescence volume, and therefore we use this coalescence volume. When deuterons and helium-3 are formed, they would probably form in a similar coalescence time, coalescence volume. So you assume coalescence volumes are the same. So therefore, if we fit the deuteron and helium-3, we can in fact independently fit RB factor and the volume factor, because they stay differently. So that's what we did. This is here deuteron, helium-3. And one thing to note is, assuming that the deuteron size is very small, obviously it underestimates the data. But if you look, deuteron size is, as long as it's larger than 1.1 Fermi, then whether we take 1.9 Fermi or very large deuteron size, it really does not matter very much, and more or less fits the data. And with the same RB and the factor and coalescence volume, the helium-3 data is more or less okay, although it underestimates the data at larger PT. But more or less the magnitude is rather well satisfied with a very simple formula with only 2 parameters, RB and coalescence volume. RB is at 0.36, it turns out. And in fact, it's similar to the feed-down effects from statistical hadronization model. And this is also more or less similar, expected the 2-dimensional volume at the chemical freeze volume. So therefore, it's more or less expected. So now we use, so therefore, if X or TCC is a molecular configuration, we expect that similar formula should work. So therefore, this is what we did. We first used the D and D star measured at lead collision, and then used D as the 2 input distribution, and then scaled them using the feed-down effect calculated from the statistical model. And then assuming that they coalesce at the same point, use the coalescence volume as we discussed. And then we have something like this. And so therefore, if X or even TCC, because the only difference between X and TCC from a molecular point of view, in a coalescence model point of view, is whether this is D star or D is a bar or just D itself, D star itself. Therefore, assuming not much difference in the chemical potential is not very large, it's high energy collision. The difference between X and TCC, assuming their molecular configuration, would be not so large. On the other hand, if TCC is compact, this is a PT distribution that we have calculated earlier, their production rate is smaller and the PT distribution is slightly different. So therefore, although this CMS collaboration measured this ratio, the X at very high PT, if they are able to measure this PT dependence altogether, then you will be able to confirm that X is indeed a molecular configuration, just like a deuteron. And if TCC at some point is also measured, then you can also check whether this has PT distribution is indeed of this or this, and then you can discriminate whether TCC is a molecular configuration or compact configuration. And if you are able to discriminate, as I said, there's really an important, very stringent constraint on the quark model dynamics, and you will be able to understand, you will have a new venue to understand the multi-quark dynamics at the hadron configurations. These are just the total yield that we have obtained by integrating. Also, we comparated with psi 2s. Statistical model gives you 0.3. and this and statistical model if they are compact, and if coalescence model is larger. So therefore, but we are still far away from the CMS data, which is a very high PP. So I think I want to summarize. I think I already spent 1 hour. So summary is can be possible configuration for quark model, and I said we can indeed do this, and by analyzing the color spin and color factor, we can probe possible compact configuration. And most exotics have heavy quarks. Let's try to explain why that is so. So therefore, heavy ion collision in axon factory, and X is most likely a molecular configuration, cannot be compact, and TCC can either compact or molecular configuration. So therefore, if you measure this, then you can, in heavy ion collision, actually measure the independence. Because of this analogy with the deuteron, we will be able to see whether X is indeed a molecular configuration, and then discriminate TCC whether this is a compact or molecular. Okay, that's all I wanted to say.